Okay, so welcome to our lesson on Chapter 9. Today we're going to do some more translations, including translations that involve the symbols for and, for or, and for if and only if. And we are also going to do a few more derived rules because it's going to make the problem sets in your in Chapter 9 way easier. They're extremely hard if you don't have these. Yeah, so let's get to it. So far, we've only been translating sentences whose connectives are the not symbol, the negation symbol, or the shortcut we've been using in Carnap, and the if-then symbol, or again, this shortcut we've been using in Carnap. But we can add our other symbols back into our translation, and it won't actually be that much harder. It's advanced in the sense that you're adding in more symbols, but really it's not any harder than what we've been doing. And we can do this both ways for when we're translating from symbols to English and also from English to symbols. Again, it's going to be basically the same as what we've been doing with our translations. We're just going to include more symbols, and you'll see even the steps that we follow are basically the same. Okay, so first let's start with going from symbols to English. So the steps again are going to be the same, just we're going to consider more potential main connectives. So you'll remember our steps for translating symbols to English are you look at the symbols, the expression that's written in the symbolic language we use. And then at first you check if it's been abbreviated. So if there's been any parentheses removed, any brackets removed. And then if it makes things easier for you, you would restore the parentheses back so that you can see the sort of chunks of the expression if you need to. And then after that, you locate the main connective of the formal sentence. If the main connective is an arrow, then you write out the main connective in English. So if it says something like if P then Q, you would write if P then Q using English. Same thing for the not symbol, where if it's not P, then you'd write it's not the case that P. You've seen all of this. And then you would keep going with the remaining expressions or untranslated connectives, starting with the main connective first, right? And then you would just do this until there are no more connectives, and then you would translate the letters like the P, the Q, the R, whatever, using the scheme of abbreviation that you've been given. So let's just add some extra steps for our other potential connectives. So it's basically the same process. If you want to, you can add back parentheses for anything that's been abbreviated. Then you locate the main connective, and then you translate the main connective. The only difference now is that we have to consider, as you'll see in step 4, step 5, and step 6, we have to consider and symbols, or symbols, and if and only if symbols. If the main connective is an and symbol, so for example, you have P and Q, then you'll write it's both the case that P and that Q. This will help using this specific language will help keep things clear for you. If the main connective is an or symbol, so that the sentence is something like P or Q, then you'll write either P or Q. It has to be at least one of these, either P or Q. And then if the main connective is the if and only if symbol, the double arrow, so that the sentence is something like P if and only if Q, then you'll write if P, then and only then Q. Again, this using this specific language is just going to make it easier for you. Again, like I said last time we were doing translations, hopefully the steps are just something that helps you out in the beginning until you get the hang of it, and then you can just kind of do it. But yeah, then you'll see the rest of the steps are all the same. You just do this for every part of the sentence, translating it main connective by main connective by main connective until you only have the letters, and then you translate the letters using the scheme of abbreviation. Now, after all those steps are completed, if you want, you can use a stylistic variation to make the English sound more natural, as long as you maintain the same logical structure. I'm going to show you a couple examples of these, but you can see chapter 9 of the textbook for a whole bunch of stylistic variations. Okay, so let's consider some examples. So suppose we have again this scheme of abbreviation from way back when we first did our translations, our first translations, where P means Plato prances, Q means Quine cringes, and R means Remy cooks ratatouille. Well, then how can we use this to do some translations from symbols to English? Well, here's a few examples. So suppose we have not Q and R. Well, the main connective here, there's no abbreviation here, so we don't need to restore any brackets. That would help us. So we move next to finding the main connective. That's step 2. The main connective here is the and symbol. We know that because if it was this negation symbol, the negation would have to be outside the brackets. So you translate the main connective. So you have both not Q and R. Or it is both the case that not Q and R. You can see I did a stylistic variation, but you should really write it is both the case that it is not Q and R. And you can see I did the long version here. So that's good. And then you translate the negation from step 1, which is it is not the case that Q and R. So you can see here I have it is both the case that, this is the translation of the and. It is not the case that, this is the translation of the negation, not the case that Q and R. And then we only have letters left, so we translate those into English using our scheme of abbreviation. And we have this awful, ugly sounding sentence. It is both the case that it is not the case that Quine cringes and Remy cooks ratatouille. Right. And then we can do this optional stylistic variant to make the English sound a lot better, which is just Quine doesn't cringe. It's not the case that Q and Remy cooks ratatouille. Right. So this is explaining everything. Okay, so here's another example. So suppose we have not Q if and only if R. Well, again, there's no abbreviations here that we need to stick brackets around or anything. So we go right to finding the main connective. In this case, it's the negation symbol. So we'll translate that first and we get it is not the case that Q if and only if R. Now we have this as our main connective, this if and only if. So we translate it and we get it is not the case that if Q then and only then R. Remember, that's how we translate the if and only if symbol. Now we only have letters left at this stage, so we translate them into English using our scheme of abbreviation. And we have it is not the case that if Quine cringes, then and only then Remy cooks ratatouille. Again, this is a really ugly sounding sentence, but it helps you chop up the bits of the sentence in a consistent way. And this is a complete translation, but I'm going to do a stylistic variant just to make it sound a bit better. And I have, it's not the case that Quine cringes if and only if Remy cooks ratatouille. Just sounds a little bit better, I think. Okay. And we'll do one more example of symbols into English. So suppose we have P and Q, or P or Q and R. I have a mistake here. Okay, so let's make sure that we know that this is supposed to be an or symbol. Okay, so again, there's no parentheses here that need to be stuck back in because it's been abbreviated. So we go right to finding the main connective. Well, the main connective is this and symbol here. So we will translate that first. And we will have, it is both the case that P or Q and R. Remembering that, this should be a or symbol, not an arrow. Well, we still have another connective. It's this or symbol here, this scribbled on or symbol. And then we translate that one. So we're going to get, it is both the case that either P or Q and R. You can see how the commas there give it a nice chunking structure. right? Well, at this point, there's no more connectives to translate, so we translate the letters, and we get, it is both the case that either Plato prances or Quine cringes, and Remy cooks ratatouille. Great. I mean, if you wanted to, you could do a stylistic variant. I guess this one is, in my view, a little bit nicer, but it doesn't really change things that much. I just have, it's both true that Plato prances or Quine cringes, and also that Remy cooks ratatouille. So there you go. And that's some examples of going from symbols to English. Okay. Now the other direction from going from symbols, from English to symbols, again, we'll have to switch these two. Here's another little error here. Should actually be going from English to symbols. Will be very familiar. So the steps from chapter 2 for English to symbols were like so. Replace all the stylistic variations on if then and it is not the case that with their if then and it is not the case that equivalents. This is going to make it easier because, you know, we'll have a more consistent language. Then you would find the main connective in the English sentence. You would replace it with the appropriate symbol. And then you would wrap that in parentheses, unless it's a negation symbol. Yeah, good. And then you would do that again for any other remaining connectives. You would find the main connective, translate it. And then you would just do this until there are sentences without connectives remaining, or little bits without connectives remaining. And then you would just replace them with the corresponding letters from our scheme of abbreviation. These exact steps will work if we include our other connectives. We just have to remember that in step 1, not only do we have to replace the stylistic variations of if then and it is not the case that, we have to replace stylistic variations of and symbol claims, of or symbol claims, and of if then, if and only if then claims. So I'll do some Carnap examples now to show you how we'll do this in our system, but it's basically the same as you've already been doing. All right. Okay, so let's do some translation practice. I have a practice document as usual in the lesson 9, and this time lesson 9 module on Brightspace. Just click on it and it should bring you to this set of practice questions, which unfortunately are just practice questions. They are not problem set questions, so you can't submit them, but they should help you when you do the problem sets. All right, so you can see I also have my notepad up on the right side there where I'll be doing my translation steps and where I've already copy pasted the scheme of abbreviation or translation key. Yeah, so let's get started. Let's consider 2.1, for example. So we'll copy that because we're going to want to translate it, put it in our notes, and we will get to work on it. So the first thing we want to do is replace stylistic variations of connectives, right? Well, we only really have one connective here. It's this but, and we have this weird sort of abbreviation going on. So we're going to translate, what is this? Well, first let's consider what this is saying. It's saying both that John is working late and that John will make supper, which are both, you know, things mentioned up here. John is working late and John will make supper. So this is going to be like an and claim, right? So we're going to say John is working late, and we're going to write this as John will make supper. That's going to make things easier for us. Well, next we want to translate the connective, the main connective, right? Well, in this case, there's only one connective. It's this and. We will replace it with an and symbol. That's great. And now we want to replace the little bits of sentences here, right, with the corresponding letters from the scheme of abbreviation, because there's no more connectives, so we can translate the bits of English, the remaining bits of English. So John is working late is Q. John will make supper is P. So we put those in. Q and P, everything is translated. Stick it back in here, and let's see if it's right. Look at that, perfect match. All right. So let's go straight to something more complicated because I know that... oh, well, let's do this one, actually. This one's kind of fun. And then we'll do another more complicated one. I know you guys have seen this kind of thing before. We've just added in a couple more operators. So hopefully it's not too difficult. Okay. So in this case, we're considering this sentence. Neither John nor Mary will make supper. What is this saying? It's saying both that John won't make supper and that Mary won't make supper, right? It's saying neither of them will. So let's rephrase this neither nor as a not P and not Q, right? So we're gonna have it is not the case that John will make supper, and it is not the case that Mary will make supper. Great. So now we want to look for the main connective. Well, it seems like and is the main connective, right? Because it is not the case that is modifying only John will make supper, and this it is not the case that is modifying only Mary will make supper. Whereas and is modifying them both. So we know it was added on last. So let's translate that. Next, we look for our next main connective. Well, we have two knots here. By the lefty-righty rule, we know it's you'll remember the lefty-righty rule from lefty-right rule or whatever it was from like chapter 2 for abbreviations. Anyway, we know by the lefty-righty rule, this rightmost knot has to be most recently added. So we will translate that one. Not Mary will make supper. And then there's only one connective left. It's this, it is not the case that. So we'll translate that. And there we go. No more connectives to translate. So we will just look for the letters that replace these sentences. So John will make supper is P. So we have not P. And Mary will make supper is R. So we have not R. And there we go. It's all translated, not P and not R. So let's stick that in here and see if it's right. Look at that, correct. Great. Okay, so let's do one more advanced one. And then I think since this hopefully is not too much new information, I can just leave you to the rest. So in this more advanced section, we have a lot more letters we could be using. So let's add those to our notes here. Of course, you could be using pencil and paper yourself, which would be good. But I am not. So let's do, I don't know, let's do 3.5. Okay. So luckily this one has no stylistic variance, it looks like. Well, we could, deficit will be raised if taxes are raised and interest rates do not rise. Well, what is this saying? It's saying that both the deficit will be reduced and the economy will improve if taxes are raised and interest rates do not rise. So it's saying if these two things happen, then this will happen. So actually, stylistic variation will take this first half to get rid of this stylistic variation, and we'll stick it on the end because the sentence is really saying, if taxes are raised and interest rates do not rise, then the deficit will be reduced and the economy will improve. So that's good. All right, so that's stylistic variation that we made more standard by making it a clear if-then. Good. All right. So what is our main connective? Well, it's clear it's the if-then because the if-then is modifying both this, taxes are raised and interest rates do not rise, and also it's modifying the deficit will be reduced and the economy will improve. So let's replace this if-then with an arrow. Okay, good. So what is the next main connective? Well, we have taxes are raised and interest rates do not rise. And we have the deficit will be reduced and the economy will improve. Well, let's do this and first, because we can tell these two ands are more recent than this do not claim, because they are modifying multiple things, where the not is only talking about the interest rates. And this second and by the lefty-righty rule has to be more recent. So we'll put an and there, and we'll put brackets around what it's modifying. This will make things easier for us. Okay, and then we have to look at this first half. We have, well, the and, as we just said, we know is more recent than the do not. So we'll put and here, and we'll put brackets around everything it is modifying. Great, okay. And then we have this do not rise. Interest rates do not rise. So it's modifying the claim that interest rates will rise. It's saying it is not the case that interest rates will rise. So let's translate it. It's not the case that interest rates will rise, right? Well, at this point, we have no more operators, or connectives. We just have sentences that are represented by letters in our scheme of abbreviation. So we'll translate those. So taxes are raised corresponds with V. So that's V. Interest rates will rise corresponds with P. So that's P. The deficit will be reduced corresponds with U. So I'll put a U there. And the economy will improve corresponds with Q. You can see up there. So we'll replace that with a Q. And there you go. You can see that this is a nice completed translation. So let's try that out. And you can see we get another perfect match. Okay, so I hope that that's enough practice with translations for you to be able to complete the relevant problem set in Chapter 9. And now I'll show you a few more derived rules that are going to be extremely important and helpful for the problem sets in the chapter. All right, so quickly before I get into showing the derived rules, just some notes that two of the problem sets in Chapter 9, problem sets 11 and 12, they want translations like what we've been doing already, but they also include some derivations that are very tricky and are made a lot easier with some more derived rules. So specifically to do these derivations, you're expected to have access to a few derived rules. You're expected to have access to the different versions of De Morgan's laws, proof by cases, and negated conditional. And I'll show you what those all are. But then, you'll have, like normally you have to prove them on your own Carnap account, like we did a few weeks ago for derived rules, and then you can deploy them in the problem sets. All right. Okay, so you can see on the right, I have our basic propositional rules, because you'll be able to see the other derived rules we might use as I prove them, and as you will have to prove them as well. But as always, when we're doing derived rules that we're going to use later, you have to click on textbook, click on index of rules, and then scroll down to derived rules. And today we're going to be proving everything here. And you are going to want to use these in your problem sets for Chapter 9. So let's start with, well, first I'll explain something to you. So this is, before I do any proving, this is just to show you something. Let's zoom in a bit, shall we? Okay. So this and this So these are two laws, theorems of formal logic. They're called De Morgan's laws because they were proved by some guy named De Morgan. And these are very standardly known in the logic world, and so it's good for you to learn them. But they're also given in some substitution forms, which are logically equivalent to those. So you'll see we have these as well. So, all right. So you'll see this is what I'm calling D-DMT 1. This one I call D-DMT. Oh no, I call this one D-DMO 1, D-DM2, and then this one I call S-DMO and S-DMT. So just so you know, so these top two are De Morgan's laws as they're normally given. So the first one is not P or Q if and only if not P and not Q. And the second one is not P and Q if and only if not P or not Q. And then these are logically equivalent substitution forms of each of them. So you can see this one is equivalent to this one, and this one is logically equivalent to this one. So we're going to prove all four. And you can see I've given them these names. The DMO is De Morgan's 1. The D is for derived rule. This one's De Morgan's 2. This one is substitution De Morgan 1. And this one is substitution De Morgan 2. So I'll show you how to prove them. You can prove them in a variety of orders, but the first one I'm actually going to prove is substitution De Morgan 1. You don't have to do it that way, I guess, but I don't know. That's just the way I did it. So this is going to make your life easier if you follow along and do it how I did. Okay, so this is what we're trying to show. P and Q if and only if not P or Q. So as usual, we have this biconditional, which means we need to prove that the left side implies the right side and the right side implies the left side. Notice we're not going to use any premises. We're just going to prove this as a theorem. So we know that we need to show that the left side implies the right side to get our biconditional, right? So we'll start with that. How do we prove a conditional? Well, we assume the left side and then we arrive at the right side. So let's assume P and Q. And then we're trying to get not P or Q, right? Well, an easy way to get a not is to assume what it's negating and show that that leads to a contradiction. So let's do that. So first we want to show not P or Q, right? Then we assume what it's negating to get a contradiction. You can see we're already a few proof nests deep. All right. Well, what do we have here? We have a P and Q, which is great because we can get P by simplification on 3, right? Remember, we have access to this line as long as it's not from a closed proof above us. And so we can get P and Q separately from this P and Q. Well, how can we get a contradiction here? We want not P or we want not Q. Well, if we can negate one side of this, we can use modus tollendo ponens to get the other side, right? You'll remember our basic rule MTP. So how can we negate one of these sides? Well, we can put a double negation on one of these P's or Q's, which we can always do when we have one. So let's do not P, double negation introduction on line 6. Then we can use that to get not Q, right? By modus tollendo ponens using line 8 and line 5. Great. Okay, but look at that. There's a contradiction. We have this not Q and this Q. So assuming not P or not Q gave us a contradiction, which means we get its negation, not P or not Q. That's an indirect derivation. The contradictions we found are from lines 7 and 9. So you'll see that closes this. We now have access to this, which means we showed that after everything, if you assume P and Q, you can show not P or Q or not Q. And so you can get the conditional derivation where if you assume the left side, you get the right side. So conditional derivation, we have access to what's on the show line now, so we could cite it, and there you go. Great, so now we've proved one side of this biconditional. We have to prove it the other direction as well. So now we want to show that the right side of this biconditional implies the left side. Well, now we assume this. Great. So how are we going to get P and Q? Well, one way to do it is to show not P and Q, and then we can get a double negation out of it, right? So if we assume not P and Q, or hold on, let's see what we can do here actually. All right, so let's reset. We're not going to do this not. We're going to show P and we're going to show Q separately, and then we can put them together, right? So if we want to show P, we can show not P, right? And we'll just have to show that not P leads to a contradiction. So if we do that, well, we assume not P. Well, look at that. We can always add whatever we want onto a atomic formula using our addition rule. So we took not P, we added a not Q. Well, look, not P or not Q is negated already. So we know that we can close this proof. Indirect derivation on 16 and 13 are the contradicting lines, which means we have not P, which means conveniently we can get P by double negation elimination on 14, which we now have access to. And then we want to do the same with Q. So we're going to show not Q, which means we assume not Q. And we can basically just do the same thing, right? Because we can put this on either side of an or statement with whatever other thing we want, because that's how our addition rule works. So we can just get not P or not Q again, this time on line 20, because that's what we have access to here, right? We're doing it with the not Q. And again, this contradicts what we have in our earlier assumption. So we can get an indirect derivation, this time on 21 and 13. You see that closes this. So we now have access to that, which means we can get Q from double negation elimination on 19. And look, now in this depth of the proof, we have P here and Q here. So we can get P and Q by adjunctification on lines 23 and 18. And there you go. So then we showed that if you assume not P or not Q, you can get P and Q. We did a conditional derivation on line 4, showing what we wanted, which was this, right? Well, now we have access to both directions of this biconditional claim. That is really what we're trying to show in the end, right? And we know that we can build a biconditional with two conditionals that we now have access to. And we'll use the rules, conditional, biconditional, and we will, now we have access to one way of the biconditional on line 2, and the other way on line 12. So we'll write that. And then look at that. That's exactly what we were trying to show in the end, right? This big, long claim. And we will point out that we have a direct derivation there on line 26. And look at that, it populates it in the rule builder. Save it. This one I call substitute De Morgan 1, so SDMO. There you go, that's the first one. All right, so now let's do De Morgan's 1. Now we have these Greek letters here, but I will, sorry for misspelling the show there. I will translate them into P's and Q's like we know we should. Okay. So again, we have a biconditional, meaning we need to show both sides of it. Right, I need to say this is a show line. Then, as always with a conditional, you assume the left side, and you try to get the right side, right? Now, what do we need? We need a not P and we need a not Q. How are we going to show those? Well, let's write that we want not P, so then we can assume P, right? And now we want to get a contradiction. Well, if we assume P, we know that we can get P or Q because we can add a or of any kind we want onto something we already have. But then look at that, this P or Q contradicts this not P or Q. So that's an indirect derivation on lines 6 and 3 are the contradicting lines, right? 6 and 3. Where have I gone wrong here? Ah, I see. So because I had an extra bracket here, that the system didn't like it. But if I get rid of that bracket, and then what's this one? Can't read line 3. Let's replace that. How's that? Is this any better if I replace everything? It's interesting. Ah, right, because I forgot to say I was assuming it. You can see I forgot to include my justification. So once I include that, then the system is happy. All right. So now I have not P. I can do the same thing as I did to get not P to get not Q. Then you assume Q. From this, you can get P or Q from line 9. And again, we have the same contradiction between P or Q and not P or Q. There you go. At this point, now we know we have not P and we have not Q, so we can just add them together. And that's with our adjunctivization rule, or adjunctivation. I can't remember the exact phrasing of it. But it's ADJ, it's the ADJ rule. And great, so you assumed not P or Q, and then you got not P and not Q. So that's a conditional derivation on line 12. There you go, you showed this side of the biconditional. Now we have to show the other side, right? Okay. You can see I've just flipped the order compared to this and made it an if-then instead of an if and only if-then. And to show this conditional, well, we always assume the left side, and we want to show the right side. How can we show the right side? Well, let's try this first. So let's assume P or Q, right? See if we can get a contradiction. Well, we have not P and we have not Q, so let's simplify those to pull them out. We have those from line 15, right? You can see we have the combination of them there, the adjunct of them there. So with these not P or this not Q, we can apply modus tollendo ponens on this or claim. to get the negation of one side of it. So let's just use not P on the P here to get Q, right? Modus tollendo ponens using lines 18 and 17. If we have the negation of one side of the or claim, we just get the other side out of it. But look, that's a contradiction. We have Q and not Q. So in that case, we know we have an indirect derivation of not P or Q. And the contradiction is on line 19 and 20. And then we've shown not P or Q, which is our conditional derivation. Look, we assumed not P and not Q, and then we got not P or Q. So we've completed the conditional derivation using this, which we now have access to, so line 16. And there you go. Now we have the conditional going both ways, which means we can make the biconditional that we've been trying to show the whole time, right? So we have two conditionals that go either way to make one biconditional. So that's conditional biconditional rule, CB rule, using lines 2 and line 14. And look, that's exactly what we were trying to prove. There it is. So that's a direct derivation on line 23. And you can see it populates the rule. All right, so this one we are calling D-DMO for De Morgan's 1. Okay, so I will just show you pictures of De Morgan's 2 and substitution De Morgan's 2, our proofs for that. They do make appeal to one of these derived rules up here, so you'll see how these come in handy for proving them. But I don't want to take up too much time in the lecture. You can just prove De Morgan's 2 and substitution De Morgan's 2 on your own using the picture I give you. So I will show that in some slides now, and you can pause and write them down and also get them on the Brightspace page with the slides. All right, so as promised, here is a sample proof of De Morgan's 2, which when you are finished proving it, you'll save as DMT, and then in the future you can use as D-DMT. So take a look at it, pause the video if you need to, understand each of the steps as you put it in to your system so you can get access to the derived rule yourself. And note that you're going to already need access to the substitution De Morgan 1 for this particular version of the proof that I give you, which I just proved in this very video. So hopefully you will have already done that proof and saved it yourself so that you could use it for this. And similarly, here's another sample proof for substitution De Morgan 2. Again, in this one, you're going to need access. If you're going to do the proof like I did it, you're going to need access to De Morgan's 1, which I also already showed in this video. So yeah, pause the video as you want. Take a look at this. And do it step by step and understand each step as you enter it in your own system. It will help you in the long run. Yeah, and now I'll go back to showing you some other derived rules. Okay, so back for the remaining derived rules, which I'm actually going to walk through because they're not De Morgan's. But you should, as I said, prove the other two De Morgan's rules. So that would be De Morgan's 2 and substitution De Morgan's 2 using the slides you just saw in video. And you can also pull them out of the slides that I post on the Brightspace. But yeah, so let's prove proof by cases, which is this one. So in this one, we actually have some premises. So we're trying to show that you can get at any R. You're just trying to show a R with the premises P arrow R, Q arrow R, and P or Q. And we'll make sure that we write that these are premises. And naturally in your head, this makes sense, right? Because if you have at least one of P or Q is true, and you know that both P and Q imply R, then you'll get R, right? But we need to prove it in our system. So let's, to get at R, let's assume not R, right? Or let's show that we can get not R by assuming R and getting a contradiction. Because if we have not R, we can get R by double negation elimination. Okay. So if we have not R, then we know through modus tollens we can get not P and we can get not Q. So let's do that. Modus tollens using the not R on line 6 and the conditional on line 2. We do the same thing. We can get not Q by modus tollens using the R on line 6 and this time the conditional on line 3. Now we also have P or Q, right? Well, with our not P, we can negate the left side and just get the right side out of it, right? That's using modus tollendo ponens. So let's do that. We can get a Q, modus tollendo ponens on line 4 and line 7, where we have our not P. But look, there's a contradiction. We have not Q and Q. So we know that if we assume not R, we get a contradiction, which means we have to have not R. This is proved using our indirect derivation, and the contradicting lines are 8 and 9. So great, now we have access to not R. Well, then we have R also by double negation elimination on 5, right? We have access to this line. We can get rid of both negations on it, giving us R. And that's exactly what we were trying to prove, right? So we have direct derivation on line 11 of what we were trying to show. So when you save that one, call it PBC for proof by cases. Yeah, there you go. And then we have one more derived rule to prove. We have this negated conditional rule. Okay. So this one, again, has no premises this time. So I will put in this. Great. Again, we need to prove the conditional both ways. So we're going to try and show it the left way first, or taking the left side and getting the right side first. How do we do that? Well, we assume not P arrow Q, and then we want to show P and not Q, right? Well, how can we do that? To get P, let's assume, or let's show not P, and show that if we have not P, we get a contradiction, right? Well, conveniently, we have this other derived rule over here, MCNA, right? See that, guys? And you know that if you have not anything, then you can get that thing implies anything else. Well, we have not P, which means we can get P implies Q, right? And we'll use our derived rule from some classes ago, D-MCNA. Whenever you use a derived rule, remember you have to put D in front of it. On line 5, right? Well, obviously that can't work because we have not P, not Q. That's a contradiction. So we can get not P, right? We assumed not P. We got P arrow Q, which contradicts with not P arrow Q. So we get an indirect derivation using lines 3 and 6, which contradict. What's the problem here? Can't read line 3. Oh, right, because I didn't say how I got it. It was assumed. All right, so I put in how I got that. It was assumed, and the system is happy with it. All right, great. So now we have not P, which means we can get P by double negation elimination on line 4. So now we have one side of this AND claim that we're trying to get. Now we need to get the other side. So let's show not Q by assuming Q, right? Because if we can show that Q leads to a contradiction, we get not Q. Well, we have this other derived rule, MCC, over here, that says if we have anything, then we can show that anything else implies it. Well, conveniently, we have Q, so we can show that P, arrow Q, using our derived rule MCC. So D-MCC on line 10, right? We have P arrow Q. But again, that contradicts what we have up here, our not P arrow Q. So that's going to give us not Q. You know, you assume Q, you get a contradiction, so you get not Q. And the contradicting lines are 11 and 3. And look at that. Now we have P on line 8. We have not Q on line 9. So we can get P and not Q by adjunctivization on 8 and 9. And that's exactly what we were trying to prove, right? If you assume not P arrow Q, then you can get P and not Q. That's a conditional derivation. Line 13 is where we got what we were trying to show. Okay, and now we need to prove it the other way. Okay, and this is what we're trying to show now. So as always, we assume the left side of the arrow, and we want to get the right side. Well, how can we get the right side? Well, we have a negation as our main connective, right? So we know that we can get that through an indirect derivation. If we want to show P implies Q, or not P implies Q, then as always, we can assume what is being negated and show it gets a contradiction. So P arrow Q, we'll assume it and see if we can get a contradiction. Well, from P and not Q, we can simplify that, can break that down. We'll get P from line 16 using simplification, S, and not Q using simplification on line 16. Oh, again, on line 16, I forgot to say I assumed it. Okay. Once I do that, everything is happy. All right, but we also have this P arrow Q and we have this P, so we can get Q by modus ponens, right? So we get Q, modus ponens using line 18 and 19. But again, here's a contradiction. Look at that. Not Q and Q contradict each other. So we have an indirect derivation of what we were trying to show. Because, you know, we assumed P arrow Q, we got a contradiction. So now, of course, we have not P arrow Q. Contradicting lines were 20 and 21. All right. And then we got exactly what we were trying to show on line 15, right? You assume P and not Q, and then you get not P arrow Q. And we did that exactly here. On 16, we assumed P and not Q. And then we were able to show that not P arrow Q. So that's a conditional derivation on line 17. You can see this is all going well. And now we did both sides of this biconditional, right? So we can use them both with our CB rule, our conditional biconditional, on line 2 and line 15. Now that we have access to those, we proved them, we have access to them, so we can use them in our CB. We get exactly what we were trying to prove. So we can close our derivation on line 24, which is where we got what we were trying to prove. You see it populates it up here. So this one I'm going to have you call negated conditional, or NC. All right. So there you go. With that, you now have access to these derived rules that are going to be important for your problem set. So I'll just go show you how to, I don't know, deploy them for one of the problem set questions. So at least you'll be able to have that one complete. Okay. Right, so you can see I've come down to problem set 12. I'm looking at question 12.1. You'll see there's some 5 questions in problem set 11 that want you to use derived rules, or it'll be a lot easier to do it if you use them. But there's 2 questions in problem set 12, and have derivations. The other questions in problem set 12 are translation. But I'll show you 12.1 so you can see how we could deploy one of these new advanced derived rules, I've called them. And you can see I've put our new derived rules on the right side of the screen for reference. Okay, so what are we trying to do here? We're trying to show R or S and Q, and we have our premises, which I will list. Of course, they all have to go on a different line, and we have to say that they are premises as usual. Okay. Well, already I know that we're going to get P implies S and S implies P because our biconditional conditional rule lets us pull those apart, right? Since we have a biconditional on line 2. So I just don't know if those will be useful later, but it's a good habit to pull things apart when you can, so you have more tools at your disposal in your derivation. Now let's look at what we have here. We have R or S and Q. Well, you know, it's not obvious how we would go about demonstrating this just from what we have here. But if you take a glance at our new advanced derived rules, you'll see that there is a rule here where our main connective is a OR. It's substitution De Morgan 2. In this case, Q or P has a biconditional relationship with not Q and not P, right? Well, over here, our main connective is this OR as well. So we can deploy it here, even though there's like something made of another connective on the right side of this OR. It's still an OR claim, just like we have here, right? So let's bring in this version of De Morgan's law. This is D-SDMT, but we're going to want to make it relevant to our case, right? So our OR claim is R or S and Q. So let's do that. Let's import that instead of Q or P. So we know that R or S and Q, if and only if, not R. And we have to make sure we're being consistent and replacing both sides here. S and Q. Right? Good. Okay. So we know that this is the case. So we know that also from our biconditional conditional rules, we can make this go both ways. And remember, we want to get R or S and Q. So if we can get all of this, right, then we can imply R or S and Q. Because we can apply the biconditional conditional rule to it. Do I have the wrong amount of brackets? I do. Okay. That fixes it. Great. So now we want to show all of this, right? Because if we can show all of this, we could use monads ponens to get this. Great. Well, our main operator here is a negation, so if we can show that assuming all of this leads to a contradiction, then we'll be golden. So let's assume all of that. From this and, we can get not R by simplification, right? And we can get not, in brackets, S and Q. Right? Good. Okay, so where can we go from here? Well, we know that with a not R, we can get P, right? Because of line 4. And we have a not R here, so let's get P by modus ponens on line 4 and 11. Well, with our P, we can get, with our P here, we can get S, right? By modus ponens on line 5. Oh, line 5 and 13. All right. Good. At this point, we start wondering where we should go next. Well, remember, we're trying to show that assuming this leads to a contradiction. So we're going to look for what we can make that will give us a contradiction. Well, we already have an S, so maybe we can get an S in Q. And if we can get an S in Q, then we can get a contradiction, right? So let's look for how we get a Q. Well, we have this not Q up here on line 3. So if we can get a negation of not P, we can get a negation of not Q, which will be not Q. And if we have not Q, we can get Q by double negation elimination. So let's see, how could we get a not Q? Well, we need a not P. Conveniently, we have P here on line 13. So we'll get not P by double negation introduction on line 13. And with that not P, we can get not Q by modus tollens using lines 15 and 3. Well, not Q gets us Q. Look at that. Double negation elimination on line 16. And finally, we have S and we have Q. So we can get something which contradicts this. We can get S and Q using adjunctivization on lines 17 and 14. And look, now we have our contradiction, right? If you assume not R and not S and Q, you get a contradiction. So then we get the negation of all that, which is what we were trying to show. In direct derivation, the contradicting lines are 18 and 12, which is great. So now we have this whole thing, which on line 8 we know gives us what we're trying to ultimately prove, right, by modus ponens. So we can get what we were trying to prove using modus ponens on line 8 and 9. Right? And look at that. This is exactly what we were trying to get, R or S and Q. So that's a direct derivation on line 20. And you can see the problem is now solved. Everything is correct. And it was made possible or easier, I guess, by deploying one of our De Morgan's laws versions, which is substitution De Morgan 2. Of course, the D means derived. But if we didn't have this, then this proof could have been a lot longer. Maybe there's even a more efficient way of proving this one. This is just how I did it. But using our derived rule let us get the proof in only 21 lines, which may sound like a lot, but there are some pretty long proofs in the problem set collections. So yeah, all right. So hopefully that's a way that you can see how these derived rules could be handy. And I guess that's the end of the lecture, really. So thanks for watching. As always, stay on top of problem sets, do practice exercises, and we'll keep moving along. All right. Thank you very much. Ask questions you have at the live sessions if you have them.